In today's session, we're going to be exploring a brand new and very interesting time series model. This particular model serves as a significant and valuable extension to the well-known VAR framework that we briefly introduced and discussed in our previous session. And as we consistently do for our practical examples and demonstrations, we will be making use of the excellent Finance Research Gate website.
However, before we proceed any further with our main discussion, it is absolutely essential that we take a moment to carefully examine and thoroughly understand both the intricate mathematical foundations and the fundamental theoretical concepts that underpin and drive the vector error correction model itself, which is, of course, the well-known error correction model derived from the vector autoregression framework.
In this particular scenario, we are specifically utilizing the lagged value of our primary variable of interest, along with the other chosen variable or the alternative series that has been selected. Furthermore, we intend to incorporate an essential equilibrium relationship correction into our model.
Our objective is to eventually conduct a thorough examination of the changes occurring in our specific target series. For example, consider a scenario where we observe two distinct yet fundamentally connected stocks. These stocks might exhibit what's known as a co-integrated relationship, meaning their price movements tend to stay aligned and consistent with each other over an extended period. In this particular scenario, we observe a clear co-integration, which signifies an equilibrium relationship existing between two or more distinct time series. Consequently, in this specific situation, employing the vector error correction model would be entirely inappropriate. For instance, if we consider two distinct stocks labeled A and B, and our goal is to meticulously examine the price dynamics of each, what would be the most appropriate and relevant equation to employ? We understand that this analysis is being conducted within the framework of a vector autoregression VAR system. Regarding the vector autoregressive model, the core concept is that it includes an autoregressive component. This implies that we are regressing the current change of a particular variable not only by its own past values, or lags, but also by the past values, or lags, of other related variables. In this particular scenario, we will be employing this specific form. The fundamental rationale behind implementing this transformation, as we have frequently reiterated on numerous occasions, is primarily to ensure that the data becomes stationary, and subsequently we proceed to fit the VAR model. The VAR model essentially utilizes the previous values or lags of the main variable we're interested in, which is y in this particular instance. It also incorporates the past changes of x, and similarly, we include the lagged changes from the other relevant variables within the model. So, let's consider stock A and then stock B. We'll calculate the daily change for each. Then we'll regress the current change of one stock by its own previous day's change and also by the previous day's change of the other security. This is how a typical VAR system is structured. It's considered vector because we're working with multiple data series, and it's autoregressive because we're incorporating the lagged values of these variables into the model. In both equations, we are using precisely the same lags. We can certainly have lags of 2, 3, 4, 5, and so on, extending further. However, for our current discussion, we're focusing on a simple VAR model. This is primarily because we are exclusively utilizing just one lag for the entire vector of our time series. The VECM will also be introducing a component that is designated as the ECT,
error correction term.
This applies to each individual instance or observation. This particular situation will hold true if these two distinct data series exhibit a clear statistical relationship or if they can be considered co-integrated, which essentially means they share a stable, enduring, long-term connection. And if there is a stable, long-term relationship between them, then any significant deviation from that established long-term or equilibrium relationship will naturally be corrected and brought back into balance. This process of correction will then induce observable and important changes within the target series itself.
So, the ECT is not about the long-run equilibrium itself, but rather the correction to that long-run equilibrium.
So, if you experience a deviation during a specific time frame, moving away from that stable equilibrium point, then we can expect certain adjustments and corrective actions to occur, ensuring the variable eventually returns to its original equilibrium state.
For example, let's say we have a spread. If the relationship for the long-run equilibrium of this spread is given by a constant value, that value could be, for instance, equal to 0.005.
So, if you take the logarithm of price B and subtract it from the logarithm of price A, we might then observe a long-term relationship where the resulting difference, specifically at the equilibrium level, is found to be equal to 0.005.
Now, does that mean that in every single period, the difference between these two securities would always be precisely equal to 0.005? The answer to that is no.
In one period, for example, you may have 0.1, 0.2, 0, or perhaps minus 0.1, or even minus 0.005.
In any situation where the observed spread is not equal to its equilibrium point, as we can see with these specific values, we will inevitably need to apply a correction. This correction is precisely what we are modeling and then integrating into our system here, because these necessary adjustments will ultimately induce significant changes in the underlying variables. If the difference between the two series, for example, truly has no bearing on anything or no real effect, regarding the y variable, specifically the observed change in one series and the corresponding change in the other series, because we are dealing with two distinct equations, if we don't have an effect, meaning that it truly doesn't matter if there's a large or a small difference, the overall spread itself is not significant and won't cause any changes. If this is the situation, then we simply don't have a VEC. But if we have a correction, this implies that we are dealing with an error correction term or an ECT term, to be precise. For instance, let's consider a scenario where the lag value of our very first data series is estimated at 4.8. The other value we're considering here is 4.6. The actual difference between these two figures comes out to be 0.2. We really need to consider taking the change, because before we can properly fit the VER model, it's absolutely necessary to ensure it's in a stationarity form. So the observed lag difference for this particular measurement is 0.002. And then for the other one, we're seeing a value of 0.001. And then moving on, we have this coefficient term presented right here. So the crucial question is, what exactly does that signify? This indicates that the current change in the x variable is determined by a function of its previous change, specifically the lag value of the same variable's change, scaled by a factor of 0.3. Consequently, we observe a clear pattern of persistence. We then add 0, which is multiplied by the change in the other variable. This means that in this specific instance, the change in x is not influenced or affected by any change in the other variable. However, for the change in z, which represents the other series, its value is determined as a function of its own previous lag, and a mere 2/10 of the change observed in that other variable, which is quite significant. This clearly indicates that the other variable exerts a noticeable influence on the fluctuations we see in this particular variable. Now the crucial question is, do we observe a significant spread or dispersion in the data? The unequivocal answer to that is yes, and its magnitude is truly enormous when compared to the actual numerical values we're dealing with. What do you think will happen if we have this spread? Let's say that the equilibrium value is 0.005. This suggests that the monetary value of this specific variable is considerably more expensive in relation to the other available variable. And in this situation, we anticipate that individuals will acquire more of the cheaper asset and simultaneously short sell the more expensive one. This action, in turn, is expected to result in a significant reduction or a noticeable decline. So, considering the change in Lx, which is the primary variable we are actively modeling and observing in this particular scenario, we fully expect its value to decrease quite noticeably as a direct consequence of that applied correction. In a very similar manner, the corresponding change in z, which represents our other significant variable, is clearly projected to increase. What will be the speed? Then the other question is, given that we have a spread, we understand the necessary correction, and we also know the precise direction of that correction for each variable in this specific scenario. But what will be the actual speed that we observe? Will this speed manifest itself within a single immediate time frame, or will it unfold across several distinct periods? The precise speed is entirely determined and dictated by these specific coefficients. Yes, it is solely through these particular coefficients that the speed is established. We have minus 0.4, and then this one is minus 0.1. That indicates that the speed of adjustment for Lx is 0.4, so it's clear that the change doesn't happen immediately. If the adjustment were to happen instantaneously, that value would be minus 0.1, and in this specific instance, it would be plus 1. But eventually, the ACE, as per the VECM model's predictions, is expected to gradually contract towards this specific point over time, ultimately reaching a stable equilibrium. So, what we have here, displayed before us, is the VECM model. And this particular section represents the VR component that we previously mentioned.
But we are leaving the correction.
To any significant deviation from the established long-run equilibrium that exists between these two distinct financial series. Now we will proceed to practically apply these important concepts and methodologies by utilizing the powerful tools available on the Finance Research Gate platform. Our initial step will be to navigate to the appropriate section and carefully select the time series analysis option. In order to apply the VECM, it is essential to select two or more data series that exhibit co-integration. This means they must possess a long-run equilibrium relationship or a stable linear combination.
So, if there is any linear combination of two or more non-stationary series, that means we can then apply the VECM. For the data, please select the monthly frequency. We'll start our analysis from the year 2000 and conclude it at the end of 2005. Then simply apply the settings.
So, I'll be selecting a pair of assets that share a close relationship. A really clear and excellent example of this connection would be soy meal and soy oil. Both of these distinct products are, in fact, directly derived from the same underlying commodity, the soybean. So, given that these two products are intrinsically linked to the same primary agricultural commodity,
Considering the overall product, the soybean, we should establish a clear connection.
First, let's start with the soy oil.
We're going to apply.
and then, at that particular moment, we are going to proceed with the careful selection of the specific soy meal.
When the soybean undergoes the crushing process, we are able to extract two main products, soy oil and soy meal. These two valuable components are directly related and interconnected because they both originate from that single source, the soybean.
Yes. Let me proceed. Click apply.
Therefore, we are now able to effectively visualize the relationship between these two distinct data series by plotting them together within a single comprehensive chart.
All right, so let's take a look at these figures. First, we have the current market price displayed here for soy oil, and then just below it, you'll find the corresponding value for soy meal. Now, what's really important to observe, if you carefully analyze the spread, the difference between these two commodities,
if you look at the relationship between them, if the observed spread doesn't display any significant trend, and instead, for example, it consistently mean reverts, then this clearly indicates that we have established an equilibrium point. It might show some deviation as time progresses, but the crucial question is, will it eventually revert to its equilibrium point? Let's examine if this specific type of co-integration relationship exists. Alright, so for the next step in our procedure, we'll need to carefully scroll down this interface, and then, from the various options presented, we must locate and select the VECM module. You must first identify and choose the two specific series you wish to work with. Now, a common query is whether we are required to transform these series to make them stationary. For the vector error correction model, or VECM, you actually don't need to do that because this particular component of the model will automatically perform the necessary differencing for you. So, in this particular scenario, we're presented with quite a few different options to consider. The crucial point is, what exactly is the nature of the equilibrium relationship that exists between all of these? Are we looking at a situation where the difference between them is essentially zero, for instance, in the case of CO? Or is it the case that we consistently observe a fixed and unchanging difference between them, similar to the specific instance that we previously brought up and discussed in this context? So the CI here specifically indicates that a deviation corrector would work to fix the mean value, and the CO, on the other hand, signifies that the overall difference between them has a mean of 0. Based on the information presented in the chart, it becomes clear that achieving a zero difference was simply not possible. The disparity was consistently present throughout the period spanning from the year 2000 to 2005. We, as a team, never once encountered any situation where we observed a complete absence of that spread. There was a consistent presence extending throughout the entire duration. Therefore, it is available for selection. It's quite probable that we are encountering a constant value which is inherently restricted or limited in its scope. Alternatively, it's possible we're observing a broader distribution or spread of deviations, one that actually exhibits a mean value that itself drifts or shifts gradually over a period of time.
So, the system will provide you with the necessary information to understand the exact situation. So, the system will tell you if there's a co-integration relationship between the two series.
The Johansen test, when applied to our data, clearly indicates that the cointegrating rank is precisely 1, which signifies that there exists a single, unique linear combination of these two distinct non-stationary time series.
The two non-stationary series are the prices of soy meal and soy oil. And yes, we have a linear combination between them. This is what the Johansen test is telling us. If R, for example, is found to be precisely equal to 0, it means that we do not have any significant cointegration, which implies that the two distinct series are simply not related to each other in a stable equilibrium relationship, and therefore we cannot effectively apply the VECM.
At this point, we can move forward since we possess a linear combination. It's conveying to us that
the crucial difference is our unique capability to actively choose and then precisely determine the specific quantity of legs.
For example, in this specific instance, we've opted for just one leg. However, in real-world applications, it's often necessary to select multiple legs. But for our current purposes, the context clearly suggests that a single leg will be adequate.
One leg would actually be quite sufficient. The cointegration rank, as expected, would certainly be 1. However, if the rank is 0 and you attempt to run the analysis, you will not achieve any valid outcome. The VEC, by its very nature, fundamentally requires a specific cointegration rank. So we selected a very specific, restricted constant, which essentially means that the average spread between these elements over the long term will consistently remain at a fixed level. Therefore, any significant deviation from that established constant level is expected to naturally revert back to its original state.
Right. So here, let's apply and put this into practice, then we can evaluate the overall impact.
Let's proceed to apply the suggested methodology so that we can thoroughly examine all the resulting findings. Following this, we will then be able to iterate on our approach and make necessary adjustments to the deterministic trend. For example, we are able to select the trend and then we'll be in a good position to put that suggestion into practice. Here, for example, we're going to examine the trend scenario.
If you go back to restricted, let's see if we can still achieve significant findings despite having restricted resources.
You know, this is where we fit the model.
We are operating with a specific pre-selected constant. Could you please explain the exact meaning of that statement in this particular context? To begin, it's crucial to understand that these values are expressed as changes. Given that we cannot directly apply the VECM to the VR model without first ensuring its stationarity, consequently, the system will first calculate the necessary difference, and then it will proceed to fit the model appropriately. So, for example, this here represents the VECM model. The current fluctuation in the price of soybean oil is primarily a function of the lagged values, specifically its own past lag, and also the lagged change in the price of soybean meal, as well, plus the error correction term, which is the ECT correction.
These are the two specific mathematical equation models that we are currently fitting. What are the values of the coefficients?
So, the ECT value we're examining here, specifically for the soy oil, is set at 0.005. This figure represents the correction factor directly associated with the ECT component. Therefore, any discrepancy or error that might arise will be automatically corrected. The speed at which that particular correction takes place is precisely indicated by alpha 1, which has a value of 0.005. For the soy meal, the adjustment occurs a little bit faster because its corresponding coefficient is indeed greater.
what about the autoregressive components that you just mentioned? Now let's direct our focus to the autoregressive component, which we'll detail right here. When we specifically analyze the soy oil variable, particularly in the context of our very first equation, we find that its previous or lagged value is associated with a coefficient of 0.2254.
And it is statistically significant at the 10% level, the observed lag in the price movement of the soy meal commodity. This particular factor is not statistically significant. However, when we consider the equation for soy meal, the delayed effect of the fluctuation in soy oil prices, the primary factor is significant at the 10% level, and its lagged value, specifically the change in soy meal, also exhibits a significant coefficient.
So, Zhao, if you were to sum these together, you would then have the two main equations. Now, this component here represents the ECT, which stands for the error correction term, or more precisely, the deviation or error stemming from the long-run co-integration relationship. So, the crucial question then becomes, what exactly is the underlying co-integration relationship that exists between these variables? It's presented right here.
This is how it can be expressed. So if you take one and multiply it by the actual price of soy oil,
We need to consider the coefficient associated with the soy meal component, whether it represents a positive or a negative value.
Mr. Storm, which is negative 3.45, and then you multiply that by the price of soy meal.
Plus the constant that will give you the long-run equilibrium relationship.
What this then implies is that if you were to take into consideration the current price of soy oil,
the current measurement shows minus 3.45.
Pertaining to the current market price of the essential soy meal commodity.
That will tell you what the relationship is between them.
Of course, since we already have a constant, we must then add that specific constant.
You understand that particular value under normal circumstances ought to be zero in the absence of any kind of deviation. Therefore, during any given period of time, if one were to take the current price of soy oil and then proceed to subtract 3.45 times the price of soy meal, and subsequently you would add this specific constant number. If there is no deviation from the plan, our result will be absolutely zero. However, if a deviation does occur, it implies that we will need to make a correction. And here we have that correction.
Here is the speed for the soy oil, and then we also have the correction speed for the soy meal.
So, if you look down here, we have the section that shows us the residuals and also the diagnostic information. This entire display is specifically related to understanding the error that's coming from the VECM module, which is quite important.
The problem is simply this section here.
Once you have successfully applied the VECM equation to this data, the resulting error or deviation is then clearly summarized here.
Once again, we are focusing on the correction speed. This particular value was simply obtained directly from the information provided within the table that's displayed right here. It represents the correction speed specifically calculated for the ECT. So, we've obtained the coefficients for all the variables within the ECT model. We also have a diagnostic for the...
And the pattern continues in that way. Now, consider this. What if we were to select two
variables that can be co-integrated?
Consequently, we are unable to effectively utilize the VECM model because if the co-integration rank is determined to be zero, which implies that there is no stable linear combination among the variables. In such a scenario, the VECM cannot be appropriately applied, and under these specific circumstances, we must instead implement the VAR model.
Of course, after transforming the time series into a stationary form, for instance, by taking the first difference.
Considering the VECM in this context, there was no requirement for us to transform the current prices of soybeans, soybean oil, and soybean meal into a stationary data series. The reason for this is quite straightforward. The VECM itself is capable of handling this task for us. Because we have a trend here, we clearly don't have the stationarity. If you go back on conducting the augmented Dickey-Fuller test, we found that the calculated p-value was, in fact, almost not statistically significant. What this essentially means for our analysis is that we are unable to confidently reject the fundamental null hypothesis, which posits the presence of non-stationarity. But the VCM will automatically correct for that, because whatever data we obtained from the table here is solely intended for the difference. Although it's not explicitly stated in the text, you see here, the accompanying notes clearly indicate that variables underwent a transformation into their difference form prior to the actual fitting of the model. And that concludes our session for today. I sincerely appreciate you taking the time to listen.